Okay, for our next problem, we have a bowling ball problem, sort of a Canadian bowling ball, small little ball. So here I have, uh, don't know if this is the size of a Canadian bowling ball, but it seems reasonable. Uh, so I have this is a ball, it's not a disc. Okay, keep that in mind. So the radius is 100 millimeters, and it's rolling down. It's going down the lane, as it were, at 5 meters per second. But lanes at bowling alleys are generally well polished and everything, and so what the person who's rolled the ball has done, note we have the normal coordinate system, uh, is put a backspin on the ball. So they've kind of chucked it down, put a backspin on the ball, so the ball is going down, but it's backspinning as it goes. So it's not exactly rolling; it's just going spinning and sliding down the bowling alley. Okay, so 5 meters per second forward, 10 radian per second backspin. Okay, uh, coefficient of kinetic friction here because it's sliding, 0.08. And the question we have before us is how long does it take the backspin to stop? All right, so, and at this time, what is Vg? So, backspin is a concept of velocity. Here's time. This is a momentum problem. And then, how fast is it going at this time? This is very much pointing to momentum. All right, so it's a ball going down. So what is its mass moment of inertia? We'll work with the centroid here, the center of mass. It's 2/5 mr squared. So 2/5 times 5 kilograms times 0.1 squared. We have 0.02 kilogram meter squared. We're all set there. Okay? So we have a momentum problem. So let's think about this. If we look at G, G is translating down because it's sliding along at the moment. So here's G in the center. We should probably just put that in there. So G is translating. All right, so we can look at, relative to G, we can actually contemplate linear momentum. So the mass of the ball, 5 kilograms, Vg1 along the x. Oh, it's 5 meters per second. So here's something that's actually spinning. It is rotating, but because the center of mass is translating here, we can apply linear momentum. Okay? This is kind of the exception to something can rotate and you can still apply linear momentum. The key is that if this were purely rotating, so G was fixed in position, wasn't sliding down the lane, then we couldn't do this. All right, so we have our initial linear momentum, and so then we can the integral of the external forces determines the secondary momentum. Well, what do we have for sum of forces here? Well, if we look along the x, all right, this thing has mass, so it's 5g coming down. That will produce a normal force of 5g going up times 0.08 will produce a force in the negative x direction. All right, so this thing is sliding, and due to friction, we have 0.08 times the normal force. Okay, and so that'll be working and working and working and working to stop this backspin, and eventually it'll stop, and then it will transition into rolling without slipping. All right, so here's our initial momentum, mvg, and so what we have for the sum of forces is simply 0.08 times n, the normal force, and that'll act for some amount of time t to produce what will be the final velocity when we convert to rolling without slipping. So here we have that. 5 kilograms times 5 meters per second. Then we have this torque that's trying to stop the backspin minus 0.08 times 5 times 9.1 times some time. So we're going to figure out the time for the backspin to stop, and then how fast is G going when that happens. All right, so we have two unknowns. We need some more information. All right, so let's see here. keep all that visible. So now we're going to apply, this thing is rolling. Okay, so I'm going to apply momentum here at G. So we have it's spinning at minus 10 radians per second initially as I'm starting to look at this. And IG, 2/5 mR squared. So boom, there we are. Minus the integral of the moments. Well, what moment is there? Well, it's the same force, 0.08 times 5 times 9.81, the weight. And then to get a moment, what's it doing? It's trying to take this clockwise, if this force had its way. And the moment arm is 0.1 meters. And I have that there. And this will go for a certain period of time. Now, here, relative to this, you could let this time go arbitrarily far. There's no real link between when this thing stops backspinning or whatever. This is just a link between time and VG2. All right? That's not the case here. All right? So here we are at 10 radians per second counterclockwise. That's a plus 10. Here's our moment. And we can let this time go an arbitrary amount of time. IG we know. I get to pick what omega 2 is. And then I can solve for the time to get to that omega 2. So I'm going to choose 0. When omega 2 is 0, the backspin stopped. We're done. So if I put that 0 here, that defines that time. Boom. Well, I can solve for that, 0.51 seconds. If I stick that back into here, that specific time, I can then solve here for VG2. And at that time, we're going down the lane at 4.6 meters per second. Problem solved. Neat little problem. Now I'll note we could do it another way. So here, so what I will take a look at is, suppose we had done, here we did it at G, nothing wrong with that. What if we had done it at A and started with that? Okay? Or we could have still done the linear momentum and gotten that equation. But suppose we started at A here. All right, you would have, why would I do that? Well, the reason you do it, if you take your momentum here, then relative to A, 0.08 newtons, there is no moment arm from the friction to A. That would eliminate all the moments. So we would actually have conservation of momentum. So let's look what happens here. So initially we have IG times omega 1. Well, that's IG was 0.02, 10 radians per second counterclockwise. So then I have a second term, R from A to G. That's 0.1 y cross mass 5. This is going 5 meters per second in the positive x direction. Okay, I know all of that. Now, when does this thing stop backspinning? Well, when omega is 0, omega 2. So IG omega 2, 0. And then I would have, for the second step, second state, 0.1 y cross 5 times VG2, which is unknown. One equation, one unknown, solve. Get VG2 is 4.6 meters per second. So we get VG2 first, and then we'd stick it into, find where I am, right into here. No VG2, solve for the time that's associated with that. Alternate way, both are good. If this was on an exam, you could have done this, then this, or do this, then that. They're all good. We've got a few more problems to do. We're getting near the end.